Good morning, everyone. Today we are going to discuss a topic called logic gates from the course Fundamentals of Digital Electronics. So, myself, Harikrishna, Associate Professor in EC Department. The key points which we are going to discuss are what is logic gate, basic logic gates, and universal gates, and the form used to represent this Boolean functions, sum of products and product of sums. These are the key points which we are going to discuss now as part of this small lecture. So let us see first what is logic gate. By definition, it is nothing but a device which acts as a building block of any digital circuit. So if you see, most of the present day technology is involving digital circuits. So in order to perform various functions in that digital circuit, we use this logic gate as a building block. So without a logic gate, today we can't expect any function to be performed by most of the smart or electronic devices. So coming to the types of logic gates, so basically there are the basic logic gates are three only, that is nothing but and, or, not gate, but in overall there are 7 logic gates. So those are nothing but, in addition to and, or, not, we have NAND, NOR, XOR and XNOR. So let us see what are these gates, how they perform their operations and how to represent them. So if you see this one, this is a AND gate. So the symbol here, what we are having is the symbol of various gates and a table called truth table. So the truth table gives information about, for different combinations of inputs, what is output, and these inputs and outputs are in the form of zeros and ones. Why? Because the logic gates deals with binary information, that means either 0 or 1. So this is a symbol of logic gates, and here fundamentally first we see about a 2 input gates. Any gate with 2 inputs, of course NOT gate is a exception for that, where it will have only single input and single output, whereas other gates, they are said to have minimum 2 inputs and 1 output. So AND gate symbol, this is AND gate symbol, and the various possible input combination, that means when we give 2 inputs, input 1 and input 2, what is the output? So this information is available in the form of a table called truth table. So with the 2 inputs, the possible combinations of total possible combinations of inputs are 4. So those are nothing but 0 0 0 1 1 0 and 1 1, and the output of AND gate will be 0. So if any one of the input is 0 and output is 1, if all the inputs are 0, so that information is available in this truth table of AND gate. And coming to OR gate, this is the symbol of OR gate, and again truth table of OR gate. So the truth table, again 4 different input combination. So this is slightly different, or we can say quite opposite to that of AND gate operation, where output is 1 if at least one input is 1 and output is 0 if all inputs are 0. So that's why the first combination only, that means when both inputs are 0, we are getting output as 0, and the remaining 3 combinations, since one of the input or both inputs are 1, we got output as 1. So this is about the nature of OR gate. Coming to this one, third one, this is called exclusive OR gate, whose behavior will be like output will be 0 if inputs are same, and output is 1 if inputs are different in case of 2 input AND gate, 2 input XOR gate. So the first combination and the last combination, if you see, both inputs are same, so that's why output is 0. Whereas second and third input combination, one input is 1, other input is 0, so that's why output is 1. Coming to the fourth gate, it is NOT gate. So NOT gate, it will have only one single input. Here, so the output will be complement of the input. So when we give input as 1, we are getting output 0, and when we give input as 0, we are getting output as 1. So this is about NOT gate. So simply the whatever the input is applied at the input, it gets complemented and available at the output of gate. That is the nature of NOT gate. And coming to NAND gate. So the NAND gate is it is nothing but a complement of AND gate operations. So in AND gate, as we have seen already, output is 0 if at least one input is 0, and output is 1 if all inputs are 1 only. Whereas this is opposite to that. So output is 1 if at least one input is 0, and output is 0 if all the inputs are 1. So that this is the symbol of NAND gate. That means for AND gate, we will add bubble at the output, so that becomes a NAND gate. So this is the truth table. And coming to NOR gate. NOR gate is again quite complement of OR gate, we can say. So OR gate, output is 1 if at least one input is 1. Whereas in NOR gate, it is opposite. So the first combination, both inputs are 0, so we are getting output as 1. And the remaining 3 combinations, one of the input is 1, so we are getting at least one of the input is 1, so we are getting output as 0. So the nature or operation of the NOR gate is opposite to that of OR gate. That's why the symbol also looks like for OR gate, if you add a bubble at the output, that means we are complementing output of OR gate to get a NOR operation. And this last one, 7th one, is exclusive NOR. Again, this is a complement of XOR gate. So in XOR gate, when both inputs are similar, we are getting output as 0. And if one of the inputs are different, then we are getting output as 1 in case of XOR gate. Whereas XNOR, it is quite opposite, because the XOR operation is complemented. So that's why the symbol also for XOR gate, we are adding a bubble at the output. So we are getting the operation like when both inputs are 0, output is 1. And when both inputs are 1, then also output is 1. When inputs are different, so we are getting output as 0. So this is about the basic, we can say, different gates and their symbol and the truth table for different gates. Then coming to another type of gates, we have of course these are not new gates, these are part of basic logic gates only, but they are called universal logic gates. Why? Because suppose if you see what are the universal logic gates means, NAND gate and NOR gate is called universal logic gates. So then the question comes, what is the that makes them universal gates? So universal gates, these two are called universal gates. The main reason is using only NAND gate or using only NOR gate, we can build any logic circuit. So, and also any logic circuit means obviously it is a combination of AND or NOT. Those are the fundamental gates or basic gates. But why these two are called universal gate means using only these two, that means either NAND or either NOR, we can construct again AND gate, OR gate or NOT gate. So no need to depend only on AND or only OR, only NOT. Only using NAND or NOR gates, we can build any logic circuit. So that's why these two are called universal gates. The main reason is you need not use AND gate. In place of AND gate, we can use NAND or NOR. You need not use OR gate. In place of OR gate, you can use NAND or NOR. You need not use NOT gate. you can use a NAND or NOR gate in place of NOT gate. So that's why using these two, one of these two gates only, you can construct any logic gates or any logic circuit. So that's why these two gates are called universal gates. So coming to the next topic, that is the representation of these logic gates. So how in the form of an equation a logic circuit can be expressed or a boolean function can be expressed. So ultimately it is a combination of logic gates only, but how it is represented, so there should be some different form. So there are two types of forms. One is sum of products form and product of sums form. So first one, let us see sum of products form. So it is one of the form used to represent a boolean function. A boolean function is nothing but again it is a combination of logic gates only. So this sum of products form is nothing but one form of expression in Boolean algebra which is used to represent the terms in the Boolean expression. So here, as the name indicates, sum of products, that means there will be different product terms and all of them will be summed up. So that is and this product or sum is with respect to Boolean algebra, not linear algebra. So that's why we call it as a Boolean algebra, Boolean functions, Boolean equations, Boolean gates, logic gates. So please remember that this is not Boolean linear algebra but Boolean algebra. So the product term is nothing but logical AND operation and the sum term is nothing but a logical OR operation. So the logical OR or logical AND operation are nothing but just now we have seen with the help of logic gates functionality and their truth table and symbol. So to understand what is this sum of product form, we need to know about something called min term. So why? Because the sum of, we are saying that one of the representation of this Boolean functions is sum of product terms or sum of product form. So product term, each product term can be a min term. So that's why we should know what is a min term. So once if you know min term, sum of product term form is nothing but also one form of sum of min terms. So here min term is nothing but which is a term with the minimum number of combinations of inputs and which is going to be true for only one combination. So if you see this table, we have 3 inputs A, B, C. That means with the 3 inputs, we will have 8 different combinations, 3 zeros to 3 ones, and the representation of 3 zeros is nothing but when it comes to sum of product form, A bar, B bar, C bar. Why? Because corresponding to A input is 0, corresponding to B input is 0, corresponding to C input is 0. So the literals or variables are said to be in the true form. Since it is we are calling it as a product form, so 0 corresponding to complemented form and 1 corresponding to normal form. So these corresponding to each of the 3 variables, since we have 0 in the first combination, M0, that means min term 0 is nothing but A bar, B bar, C bar. Similarly, for example, if you see 101 combination, corresponding to A it is 1, for B 0 and for C 1. So that's why since it is representing equivalent number 5, so it is called min term number 5 and the representation is nothing but A normal form or A is having 1. So A, B is having 0 correspondingly, so complemented form B bar, whereas C again normal form 1, so normal form. So A, B bar, C. Okay, so that is how the different combinations of min terms are represented. So product term is also nothing but a min term. So once if the min terms are known, for example, now here we have one expression, Boolean expression, f equal to sum of m1, m2, m3, m5. That means it is nothing but a sum of min terms 1, 2, 3, 5. So it is also represented like this, and it is nothing but because it is summation m1 plus m2 plus m3 plus m5, and in the form of the original table, m1 is nothing but a bar b bar c, m2 is nothing but a bar b c bar, that means 1 0 1 0, and m3 is nothing but 0 1 1, that means a bar b c, and last m5 nothing but 101, which is nothing but a b bar c. This is one form of representation of a Boolean expression called sum of product form, where the product term is represented with the help of min term, where min term, in each min term we will have each variable either in true form or complemented form. Now coming to the another type of representation called product of sums. So this is quite opposite to that of, or we can say complement of sum of product form. Okay, so and the representation also different, that means complement compared to sum of product form. So in sum of product form we have min terms, whereas in product of sums we have max terms. So that means this, as the name indicates, it is a product of sum terms. So that sum term is called max term. Each individual term is here called max term. So the representation of this max term is the truth table. If you observe, so the 3 input variables table starting from all zeros to all ones is here, and the representation is previously in min term it is small m naught, whereas here it is capital M naught, and there it is, if suppose 100, corresponding term is a b bar c bar, whereas here it is opposite, that means 1 corresponds to complemented form and 0 corresponds to true form. So that's why 100 is written as a bar r with b bar r with c. So like that are the remaining terms. So the max terms, sum of product and product of sums. So here each max term is a sum term, and we are going to product all of them. And again, please remember here the sum means not algebraic sum and product means not algebraic sum. It is a Boolean sum and Boolean multiplication. So it is a and as well as or operations are used here. So one example, if you see an expression, a Boolean expression, which is given as a sum in the form of function f equal to product of m0, m4, m6, m7. That means this f is a Boolean expression which is nothing but a product of max terms m0, m4, m6 and m7. So the same thing can be written as f equal to m0 and with m4 and with m6 and with m7. So why? Because it is a product of sums. The sums are in the form of max terms. So m0, m4, m6 and m7. And again the same thing can be written as m0 means what? Equivalent is a r with b r with c, and m4 that means 100. So one corresponding variable will be in complemented form, and 00 corresponding variables will be in the true form. So similarly 6 means 110. So a bar, b bar, r with the c, and last m7, that means all the 3 variables corresponding value is 1. So we have mentioned it as a bar r with b bar r with c bar. So this is a simple basic representation of Boolean functions, which is nothing but sum of products and a product of sums. So just as a summary, what we have covered, if you see, we have seen the definition of logic gate, Okay, then we have seen what are the various logic gates, and in logic gates there are two gates called universal gates, NAND and NOR. We have seen about their functionality and truth table and the symbolic representation of those gates. Of course, not only universal gate, other gates as well. And since these logic gates are going to be part of any digital circuit or any Boolean function, so there are basically two types of representations called sum of products form as well as product of sums. So which is discussed here. So this is about a small topic called logic gates in the subject called fundamentals of digital logic or digital electronics. So thank you. More points we will discuss in the coming videos.
Like, share and subscribe. Hit the bell icon for more updates.